Today we're going to jump in and just kind of continue our notes from the previous podcast, and we're going to jump in with dissociation constants. All right, we're going to look at dissociation constants for water and for acids. So as far as dissociation constants go, it's going to just kind of be a rehashing of equilibrium constants from our last unit. And we're going to solve them the same way, but we're going to get a couple of extra steps to find out pH values and just what the concentrations really mean. So the first one we're going to look at simply is water. And water, typically just a reaction for water, we might do something like this. H2O as a liquid. If we have two of them, they separate into hydronium ion, and we're just going to say that's aqueous, and hydroxide ion, which is aqueous. Alright, so that is just a balanced equation for what happens with water. And if we were to look at this, we would say this is very small going this direction, and really big going back this direction. Okay, so hardly any hydronium and hydroxide are made, but there's mostly our water molecules stay intact. So if we write a K for this, an equilibrium constant, then this is really going to end up being Kw. We're going to have hydronium concentration times hydroxide concentration. And just as a reminder from last unit, because this is a liquid, it's a pure liquid, we're not going to be dividing that. So our Kw is simply hydronium concentration to the first, hydroxide concentration to the first, and this is a constant such that the sum of these two things, or the product of these two things, is always 1.0 times 10 to the negative 14th. And this is true at 25 degrees Celsius. You're going to have some homework coming up. I'm not sure it's tomorrow. It might be in a couple days. But if the temperature is not 25 degrees Celsius, what are our constants for hydronium and hydroxide? And we're going to find if it's above 25, our water is really kind of acidic, and if it's below, it's kind of basic. There's going to be one of those two things. All right, and kind of just a rationale for that. And that's pretty much water. Okay. Our next thing then is going to be acids. And for acids, they kind of come in two varieties. We can either have a strong acid or a weak acid. And if we have a strong acid, it is known as a strong acid by the fact that it basically dissociates 100%. So 100% dissociation. Dissociation. Alright? So, these again, we've listed this several times, but hydrochloric, hydrobromic, hydroiodic, sulfuric, nitric, and another great one to know is going to be perchloric. Alright? So, the first five, you got to know. It's probably not bad to know the sixth one as well. But if we were to just write some acid, okay, so it's just going to be represented HA, where this anion is chloride, bromide, iodide, sulfate, nitrate, perchlorate. So we have HA plus water, and this is going to yield hydronium ion and whatever that anion is. Alright? And we're going to say, really this isn't much equilibrium, because it's going to be 99.999% forward and maybe a little bit coming reverse. So if we set up an ice table, alright, and let's say we have a 0.5 molar solution. Because this is a pure liquid, it's not going to really matter. We have 0 hydronium to start with, 0 anion to start with. Because it is basically 100%, we're going to say this is basically minus 0.5. Alright, so x is going to be 0.5. So this is going to be plus 0.5. Anion is going to be plus 0.5. This becomes essentially 0, or approximately 0. plus 0.5 plus 0.5. Okay? And again, if we look at the Ka of this, or the K value for this, then it's going to end up being a Ka, because it's acid. Kas are always going to be hydronium, or you might just write H plus if you want to kind of shorten it, times our anion, all divided by Ha. Okay, so in this case, if we put numbers in, we're going to have 0.5 times 0.5, and instead of really being divided by 0, this is going to be practically 0, or it's going to be a really, 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 really small number. Okay, so we're going to say approximately 0, or you might just say really small. So if this is a really small number in the denominator, it's going to give us a very large Ka value. Okay, so the Ka values of strong acids are really, really large numbers, such that in the textbook they won't even write them because it's impractical because they're so large. All right. So really, what we're concerned about is the Kas of weak acids. So that's going to be number 2. And weak acids are just where it's less than 100% dissociation. It might be kind of close to it, but it's certainly less than. And there are going to be values that are going to be printed in books. So again, we're going to have the same equation, Ha plus water is going to yield, well, this is certainly equilibrium, and let's just write Ha plus A minus this time. Alright, so instead of hydronium, we're just going to write hydrogen ion. And again, we're going to set up an ice table. Alright, and we'll say 0.5 molar again. This doesn't matter. This is 0, this is 0. But now, it's not going to dissociate 100%, so it's going to be X. We're going to get positive X hydrogens and positive X anions. So at equilibrium, we're going to have 0.5 minus X, we're going to have X, we're going to have X. And again, if we set this equation up, our Ka for this one, it's going to still be H plus times A minus divided by HA. But it's really going to be X times X over 0.5 minus X. We're going to find that these give us very small numbers. Alright, and these numbers can be found on page 657 of your book. It's a table, and it just lists these values, and again, they are quite small. So we're going to go from here and just jump right into an example, and you'll kind of see what we do with these. So our example is going to be, let's see, find equilibrium concentrations for all species, or if you want to put substances, anything like that, find equilibrium concentrations for all species, and the pH and pH for a 0.10 molar HCN solution. Alright? So it's an acid, it starts with an H. It's not one of our strong ones, which means it has to be a weak acid. So if we go ahead and write this out, we're going to have HCN plus water. And obviously it is going to yield H3O plus, or just H plus, and cyanide ion. Set up an ice table. We start with 0.1 molar acid. Our water's not going to matter. 0 and 0. It doesn't dissociate 100%, so it's going to be X plus X plus X. And at the end, we have 0.1 minus X. We have X, and we have X. All right? So if we look this up on page 657, we're going to find that the Ka value for HCN is 4.9 times 10 to the negative 10th. Okay? So we're going to set that equal to x times x, or it's going to end up being x squared, all over 0.1 minus x. Okay? So what are these two? These are our products divided by our reactant. Okay? And again, water is not listed because it is a pure liquid. So with this, we can solve for x, and again, kind of using our hint from last time, we're going to assume that this x is really small. all right, that the change is not much. And if it's really small, 0.1 minus this change is essentially going to give us 0.1. So again, we're going to ignore that. So really, we're going to say this is equal to x squared over 0.1. So we're going to multiply both sides by 0.1 and then take the square root of it. And we're going to find that x equals, right here, 7 times 10 to the negative 6th. All right? So kind of just finishing up kind of our question, find the equilibrium concentration for all our species. So we have a couple things. We have HCN, we have water, we have H+, and we have Cn minus. All right, so for HCN, at equilibrium, we have 0.1 minus x, or really 0.1 minus 0.000007. So essentially, we have 0.1 molar of HCN at equilibrium. All right, it's not going to change. And then what about our H2O? I'm sorry, our H plus and Cn? They are both x. So both of these have concentrations of 7.0 times 10 to the negative 6th. All right. And then lastly, our water is going to be fairly negligible because it doesn't change. So this one I'll just put non-applicable. Okay. So then lastly, we also want to know the pH. What is the pH for this solution? A 0.1 molar hydrocyanic, no, what is that going to be? Cyanic acid solution. All right. So notice that we have the concentration of H+. So pH equals negative log of H+, all right, which is what our homework has been the last days. So if we just take the negative log of this, we find that the pH of our solution is basically 5.15. We're going to do that again. 5.15 is the pH, which is acidic. It's a very strong acidic. It's not very strong acidic, just slightly below 7. And that is how you can get pHs from equilibrium concentrations as well as Ka values, which will either be provided for you or you should be able to find those on page 657. All right, and that is it for the podcast tonight. Kind of short, and we'll get into this more in class.